Hello, today I'll be discussing Lab 2 titled Lines of Charge. The purpose of this experiment is to observe, model, and analyze the properties of a charge piece of Scotch tape, where the key difference between this lab and the previous is that we'll be treating the tape as a line of n number of point charges evenly distributed throughout the length of the tape, in contrast to treating the tape as a single point charge located at its center of mass. The fundamental principles used will be the same, being Newton's second law, the electric or Coulomb force, and its relation to the electric field of point charges. Newton's second law is written as the net force is equal to mass times acceleration, where we have two forces acting on our tape, the gravitational force and the electric force. Looking at the electric force, it has two main components, the electric field of point charges, E, as well as Q, where this Q is the charge of the observed particle, and the Q in the electric field of point charges formula is the charge of the source of the force. After creating the charge tape, I did a series of tests to determine its properties, as listed here, and collected data used in the previous and now current model. Here it's important to note that tape B is our system, and the surroundings will be tape A, which produces an electric force in the positive y direction, and the Earth, which produces a gravitational force in the negative y direction. By Newton's second law, that we know these forces as vectors will sum to zero, as there's no acceleration. And that also means that the magnitude of these forces must be equivalent. Knowing this, we're able to solve for Q, the charge of one piece of Scotch tape. The model was created using the observations as well as following two key assumptions. First, we're treating each tape as a line of n-point charges evenly distributed throughout. Second, we're assuming that each tape has the same distribution and magnitude of charge. Here, pulling up the model, first important thing to note is our physical constant, which we have the electric constant and gravitational constant. Next, we have from our observations the length of the tape, which I used to compute the mass of the tape using easy conversion. Here we have the net charge of one tape, which we estimated initially to be the same value as in the first lab, which I had to reduce until I got this value, 1 times 10 to the negative 8, in order to make the magnitudes of the electric force and gravitational force be equal for the reason I discussed previously. Here we have the same function for the electric field I had previously, where it takes in the charged particle and the observation location, which I used to calculate R, and with all the other values known, we're able to calculate the electric field E. Here's a function which we use to create two objects, which consist of n number of point charges, where we have n set to 10. In general, as this value of n increases, the estimate for our value for Q should be more accurate. Last important part here is the for loop, which we use to iterate through each section of the tape, which we have represented as a point charge, calculating the vectors for their respective electric field and electric force, and then adding up those vectors to get a net electric force, which we have represented by a white arrow, and we have a yellow arrow representing the gravitational force, where their magnitudes are essentially the same, the green arrows being the respective electric field of each individual point charge. Alright, closing things out, let's consider the different values of Q we got in each lab. For the first lab, we got 1.65 times 10 to the negative 8 coulombs. For the second lab, we have 1 times 10 to the negative 8. So the big question here we want to ask is why these values are different and which is more accurate. To do this, we look at the difference in our assumptions. The reason we're getting different values for Q is because we're treating the tape as a series of point charges rather than combining them into a single point charge at the center of mass. As for which one is accurate, it seems to make more sense that the value that we calculate for this lab would be more accurate, as it more closely resembles the situation in reality. the charge property of the tape is going to be a result of a distributed charge. It's not going to be just centered at one location. However, we also must take into account that both models fail to consider that the point charges are not perfectly evenly distributed throughout the tape. So neither actually calculates the true value of Q, with the second variable still being the most accurate though. And with that, thank you for watching and hope you have a great day.